I think we can start from.
Yeah, okay.
Let's, are we rolling? Yes. Okay, welcome everyone to our last session on the last day before the strikes, train strikes. So I'm very appreciative that you all are here, and our morals are high. And if they are not, we are hiding that fact well. We have the pleasure to hear Pietro tell us about islands in AdS-CFT. ICFT.
Thank you. Thank you very much for letting me speak at this very nice conference. So, yeah, in this presentation I wanted to talk about some issues of unitarity in quantum gravity, which was also discussed by Julian, but actually in this case we will touch more the black hole information paradox. And this presentation is based on this work which came out in February in collaboration with Eric Anus, Marco Mineri, and Julian Sandler. And I try to be very pedagogical, so there are going to be a lot of pictures, not a lot of equations, but in case you're interested in details, let me know. So, what are we talking about? The black hole information paradox. What is it? In the 70s, Hawking and Bekenstein realized that black holes can be thought as thermal objects, which, with a semi-classical analysis, can be associated an entropy, which can be computed as the area of the event horizon divided by 4G. And also, Hawking realized, again using a semi-classical approximation, that black holes radiate a thermal radiation at a specific temperature, and because of this, they can evaporate. And this is in contrast with unitarity, because if we, for example, take a pure state in a gravitational theory made of many particles, and we let them collapse to create a black hole, and then subsequently the black hole evaporate, at the beginning I start with a pure state, and at the end I have a mixed state because it's a thermal state. And this is in contrast with a unitary evolution, because the unitary evolution maps pure states into pure states. So one possibility, which was proposed by Hawking, is that somehow quantum gravity loses information. So the evolution in quantum gravity is not unitary. However, it could also happen that the evolution is unitary, and the radiation that is emitted by the black hole seems thermal, but is not exactly thermal, such that in the evolution, the end state is a pure state. And of course, it would be great if we had the technology to, and a microscopic understanding of the theory, to really follow this time evolution and show that it's unitary, but it's too hard. So this is why in 1993, Don Page proposed an observable, which is the entanglement entropy of the radiation and of the black hole, because we can basically consider a partition of the system into the Hilbert space of the black hole and of the radiation. And if we trace out, if the evolution is unitary, throughout the whole evolution, if we trace out the degrees of freedom of one of the two, we get a mixed state in the other system, but the entanglement entropy of the two should be the same. That's just a fact of quantum mechanics.
So can I ask a very naive question here? So
sure.
When you have radiation coming out, eventually that will interact with some other, radiation of the universe or stars, whatever. Doesn't that destroy unitarity?
Well, yeah, but somehow we are making a thought experiment where there is only the radiation that comes out of the black hole. I mean, I just consider basically massless fields that come out of the black hole, and I just keep that as my complete Hilbert space. Could also be more than one field. For example, we could have photons or also other fields, and I think the black hole would radiate in all the modes, but in the end, all of that is the radiation that I'm thinking of.
Why would you say that the unitarity is lost with interaction?
Well, I mean, because in one of these pictures it was like, okay, it radiates, but it's not really thermal, and in the end you get a pure state. But if that radiation that came out has interacted with something else.
No, but you always think of it's like a whole universe.
Yeah, no, well, okay. Yeah.
I mean, what the proposal of Hawking was, I guess.
Yeah, no, I mean, if you assume that there's only the black hole there, then of course. if you assume that there's only the black hole there, then of course it's fine, but after all something also fell into the black hole, so I don't know.
Well, but the end state is always that the black hole is completely evaporated.
The black hole is gone, and the question is, did information just get lost, or is it somehow recorded?
Yeah, no, I understand that, but I'm just saying that if there's not only the black hole, but something else as well that it interacts with.
But let's say that you can measure everything in the universe. You keep track of all of it.
Yeah,
Information.
but maybe that's where I mean, it's similar to the measurement problem then, right? When does the wave function collapse and all that. But anyway, what I said, it was a naive question, so it probably was.
No, but, so, okay, then the issue now is that if the evolution is unitary, we would like to find a way to compute this page curve. And since AdS, of course, these two are valid possibilities, but since AdS-CFT has been proposed, I think that the vast majority of the community thinks that the second one is the possibility that it is realized. Because if AdS-CFT is correct, then a quantum gravity in AdS should be dual to a conformal field theory, which is unitary. So by construction, also the quantum gravity in AdS should be unitary. And then by extension, then we think that all theory of quantum gravity in all backgrounds should be unitary. But then the problem, yeah.
So like, okay, I understand this picture of the AdS-CFT that why this has to be unitary. But what if we live in the Caesar space? And like a lot of people have argued that the Caesar has some like non-unitary illusion or something like that. So what if we are certain of that scenario?
Well, I think that in that case, the problem is that in the sitter you also have horizons, like observer horizons for the sitter. And I think that in that case, I mean, if you, I don't think that they would argue that if you take a global metric for the sitter, that would be non-unitary. I think it becomes non-unitary only if you look at the specific metric in which you have an observer horizon, and then in that case you have information that falls into this horizon. But this is on like it's not like a black hole horizon. It's more like a coordinate horizon. But it's an interesting possibility because, for example, for flat space and for the sitter, we still don't know how to construct a holographic theory. There are, of course, proposals, but it's not as developed as AdS-CFT. And okay, so a lot of recent progress has come considering the black hole information paradox in AdS-CFT. And how can we do that? Well, until the sitter behaves somehow like a box. So if you put a black hole inside, then the radiation starts going out. It reaches the boundary of AdS, and then it can be reflected back and falls back into the black hole. So if you just put the black hole in AdS, it doesn't evaporate. Now, the way out was to consider a flat path coupled to the boundary of AdS, such that we can collect radiation into that. And
sorry, I'm completely not an expert in this, and not even an amateur in this. But I mean, why would the bounce back radiation go back to forming a black hole? It can, or does it always collapse into a black hole?
No, it's just that like you have a black hole, and then it emits radiation, and it reaches the boundary, and at the boundary you have to put the boundary condition. And usually what people put are briefly boundary conditions, so you get a radiation which is reflected back and falls back into the black hole, which did not have enough time to evaporate.
I see, but then couldn't you place the black hole somewhere else so that it doesn't fall back exactly there, but kind of makes a soup, which is not a black hole, or does it always? Maybe it's a silly question. Does it always go back? Or it may be too difficult to compute.
I think it's too difficult to compute.
I think the first statement you can make though is that the thing that dominates the thermodynamic ensemble is a black. Thermodynamic is stable, and it's a black hole in the center of AdS, surrounded by a bath of radiation. That's the most intractably favored state.
I see.
That you can actually calculate. Unlike in flat space where the black hole gets smaller and smaller to the dash. That has negative specific I think that's the main difference. Is that
So it has to be in the center because of.
Yeah, I'm not aware of
Okay.
this kind of.
It's an active area of research what exactly becomes a black hole in AdS, but I think most people believe that because of this fact, most people believe that the end of the day will end up.
Thank you.
Okay, so the idea is just to couple the boundary to a flat path and to collect radiation there, so that we can measure, for example, the entanglement entropy of the radiation, and see whether it at the end the page curve is consistent with unitarity or not. Now, what was proposed in 2019 was to compute the black hole entanglement entropy with this formula, which is slightly different than what Hawking would have computed, and it was motivated in holography. And it's basically, if people know, it's a modification of the standard U-90 formula, and it's not, as I was saying, quite the one that Hawking used, because Hawking would have computed it as the area of the event horizon vector for G. What is being proposed is that you actually have to extremize a functional between all surfaces close to the event horizon, and you have to take the minimum of this functional, which is the area of this surface plus the entanglement entropy of the matter fields between the bulk and this surface. If you can find a minimum for this functional, this is called a quantum extremal surface, what people call quantum extremal surface. And the inside of this this surface is what people call the island. While here we have the radiation that collects, sorry, the region which I call R, which collects the radiation. Now, why is this way of computing the black hole entanglement entropy interesting? Because actually it reproduces the page curve for a black hole consistent with unitarity. Because at early time, when the black hole is collapsing and at the first stages of its life, actually we try to minimize that formula, and the minimization is not successful in the sense that the surface which minimized is empty. So we have to take the area here is just 0, and we have to take all the fields in the bulk. And if we do that, then this by construction is equal to the entanglement entropy of the region in the radiation. And so at early stages, this is consistent with unitarity. However, at late times, what happens is that a new stratum dominates, and we can find this quantum extremal surface, which, if we compute, starts basically makes the entanglement entropy of the black hole going down, consistently with unitarity. However, because these fields are not considered in the radiation, the entanglement entropy of the radiation is still rising as Hawking computed it, and so this is starting not to be consistent with unitarity. So how could we fix this? Well, what has been proposed is also to change the way in which we compute the entanglement entropy of the radiation in this way. So also to include this extremization procedure, including also the area of the island, and including in the entanglement entropy of the radiation, not only the fields in this R region, but also inside the island. And the question is, well, why would you do that? And well, there was an argument and a proof, specifically in JT gravity, by Hartmann, Maldacena, Shagulian, and people in this paper here. But we will actually try to motivate why you would compute the entanglement entropy of the radiation in this way from a different perspective. And in particular, we will focus not really on this side here, but mostly on why you should include also the entanglement entropy of the field of the excitation inside the island. And to do that, we embed basically this construction into a higher AdS. Now, what I said conceptually holds for any dimension, but we will focus on, in this picture here, AdS2 and this bath here, so it's a CFT2. And this can be embedded into AdS3, considering what people call boundary conformal field theory. Because if we consider a boundary conformal field theory, in this case a two-dimensional one, then the holographic dual is supposed to be AdS3, but at some point cut at a position where the geometry stops, where I have a brane of constant tension. And this was proposed by many people here. And why is this interesting? Because if I consider this theory on this two-dimensional brain, the gravitational theory, which some people call the Randall syndrome scenario, is basically an AdS2 coupled here to a flat path, which is basically exactly this this picture here. And okay, so always have in mind that in this picture we have three ways of looking at it. One is a boundary conformal field theory, one is an AdS cap at the region, and one of a brane coupled to a flat path. And by the way, this brane attaches to the boundary at an angle, not at a right angle, but at a different angle, which is connected, for example, with the boundary entropy that also Zohar was mentioning for a defect. And why is this interesting? Well, because I can easily compute entanglement entities in AdS3 using what I was before calling the RT prescription. Because in holography, if we want to compute the entanglement entropy of a region, we just consider the geodesic, the minimal geodesic, and compute its length divided by 4g. And that's the prescription in AdS3 to compute entanglement entropies. And here we already see kind of why an island forms, because sometimes if I want to compute the entanglement entropy in the R region here, it can happen that the geodesic attaches to this brane and creates this, this island here. And this is the 3D picture. The 2D one, I am basically using this island formula where I have to basically consider CFT fields, which represent my radiation, here coupled to gravity, and here that I collect them in the bath. And I fix this point here, basically defining my radiation region. And here I just have to extremize the entanglement entropy for matter fields. And here we see why we should also include the island here, because of course to do this two-point function I need both points, so the island and the radiation region. And in this case, this area here is not present because here we are in two dimensions, so this is only a point, and the area is just 0. So this is why it doesn't play any role. So
if you didn't have a brain that you just connect 2 points in the boundary, or just in the boundary.
Exactly, but the point is that yeah, but it's a matter of where is the region that you want to consider. So, for example, you could be interested in, for example, an interval from here to here. So you will have 2 points here, and you will need to understand which one is the minimal geodesic, either this one or 2 disconnected geodesic here, for example. And so you compute this. So you compute this entanglement entropy of the matter field in this way, and you also compute them in this other way here that I was showing before. And if you check if they match, and actually they do match. And this is nice because it's a motivation for this island formula, at least in this brain world perspective. But on the other hand, it's not very surprising, because if we phrase everything in terms of this boundary conformal field theory, then these entanglement entropies can be computed computing correlation functions. And for example, in a thermal state, so this is a thermal state in Euclidean signature, so we have compactified time. Basically, we're just computing a 2-point function, which with a conformal transformation can be brought into a 2-point function with a flat defect. And at early times, we can also, for example, expand them in conformal channels. And at early times, these 2 points are very close to each other. And so what it dominates is this 2-point function in just a standard CFT2, because the boundary is too far away. And so it's specified by the symmetries because it's just a 2-point function in a CFT2. While at late times, these points get very far away and close to the boundary, so that the 2-point function is well approximated by 2 1-point functions, which again in a BCFT are specified by the symmetries. And so this island prescription, yes, it works, but on the other hand, for this simple setting that I was showing you, it's a bit too simple. We're not really proving the fact that these two should be the same. Everything was specified by the symmetries of the system. So what we thought was to try to complicate a bit this picture, and to consider, to try to understand what is the setting that gives the maximum amount of symmetry. Yes?
I'm very sorry to make that. So like, because the IR prescription people use now is not typically just has nothing to do with Mutaka-Yanagi, or it's...
I mean, to some extent, yes, it has to. It does, in the sense that this, for example, is the no, this one. The one for the black hole is Ryota-Kayanagi, but somehow modified with this, with also this term here, which was proposed by these people. And the one for the entire entropy of the radiation, no, I don't think it does, unless you want to look at it in this picture here. So what people say is that the island in D dimension is equal to the RT in D+1 dimension for this reason. Embedding it into a higher space.
Can I just ask? So
yeah.
What's the motivation for doing this? So are you expecting this embedding with the brain construction and so forth to buy you anything, or are you just doing this to motivate the island?
Yeah, because computing this, well, the nice thing is that I can motivate why I have to introduce also the matter fields inside the island. So one thing is a motivation. And the second thing is because it's much easier to compute this geodesics here, and this is why people actually most of the time compute this geodesic here.
Because the path somehow gives you natural and well-controlled path compared to the one.
Sorry.
Is it because the path, the BCT gives you natural path?
Well, I think it's because. In 2D, maybe you don't really see this difference, but in higher D, there's not a universal formula for the entropy of a CFT, for example, a three-dimensional CFT. And instead, this gives a well-defined prescription to compute it. And so, basically, we try to consider the most general setting that displays the same set of symmetries, and we came up with the idea that it's an interface CFT. From the bulk perspective. So what is an interface CFT? It's not a boundary conformal field theory, so conformal field theory with a boundary, but actually at the defect we couple another CFT with possibly a different central charge. And the bulk dual is supposed to be two AdS spaces coupled and glued at this brane with constant tension. And in particular, to understand where is this brane, you just have to minimize this the action, the bulk action, which here we have the constant tension brane. And notice that also here we have these branes which do not attach to the boundary at right angle, but actually we have this psi1 and psi2, which depend on this tension here, which again is connected with the boundary entropy of the defect. And as previously, we can compute the geodesic that connects in this case 2 points, because the radiation region in this case are the two bats here. And the brane wall will be the tension, the brane here of constant tension. And this geodesic has the nice property that it can be computed analytically, and it's just solving a geometry problem, because the geodesic here has to be continuous, and the derivative has to be continuous, and geodesic in AdS3 are just circles. So basically, we could compute this analytically, solving this nice geometrical problem. And just to show the fact that we can do it, this is the distance, and it depends on these geometrical parameters R and R, which basically are the radiuses of these two circles. And they depend also on these angles here, which are this theta and this phi. Now this, I of course don't want you to understand this formula, just to say that it's possible to actually compute exactly what is the distance of, the length of this geodesic. And it can be connected with black holes doing conformal transformation and starting from the vacuum and reaching the thermofield double state. So here where we have the time compactified, this is Euclidean time. And indeed, we can basically compute the page curve using these geodesics basically. The orange one is is basically the standard settler of the radiation, while the island settler is this blue one here. And this is the Euclidean time, while this is the Lorentzian time. So this is very nice. In this case, for example, the black hole radiates into two modes, which are collected into these two vats. And the question is now, why is this a little bit more interesting is that in this case, the 2-point function before becomes a 4-point function. And at early times, as before, what is dominant is this 2-point function here, which is, again, specified by the symmetries. But at late times is this other 2-point function, so a 2-point function of between two twist operators across the defect. And this is not specified by the symmetries. So if we can match this with the brainwave's perspective, it's a better motivation of why these two quantities, so the geodesic and the Allen prescription works. And you can do that. So this is these are the geodesics. This is the brainwave perspective in which you have integrated out all the degrees of freedom of the bulk. And basically you have these radiation regions, and these fields here, this interval here is the Allen that you want to externalize. And again, the entanglement entropy of the radiation in this case is this horrible formula here that we have to minimize over the position of these points. You minimize it and discover that actually it agrees with our previous computation. So this is a rather non-trivial test because, well, first of all, because these formula at first don't really look alike, but in the end, if you really check in the large extension limit, they agree. And also because these formulas are not specified by the symmetry. So the fact that also the dynamics is similar, actually it's the same. It's a rather non-trivial motivation to believe the Allen formula in this brainwave perspective. So these are my conclusions. So this work was basically a test of the Allen formula in this brainwave perspective, and that I also said before, and also something that we were quite happy about is that you can also motivate the Allen transition as somehow the transition of the entanglement entropy between two intervals. So the fact that at some point in the entanglement entropy of two intervals you have these sort of transitions which remind you of a page curve. And somehow in this picture here you can clearly see that what's going on is very similar. So yeah, thank you very much.
Are there any questions for Pietro?
So can I ask you about this picture that you also mentioned, which I naively asked about before, but you said there was another idea that it's not really thermal radiation coming out, but it's some other state. So what's wrong with that scenario?
No, that is the scenario that actually should happen in if the evolution is unitary.
Right.
And the problem is that you don't really know, if you compute things in the way Hawking would have computed it, you don't really see this modification between from a thermal radiation, and you don't really know how to compute the microscopic evolution.
The other day we heard this talk about the 1D black hole where it looked like you get a thermal the thermal distribution even though it should not be, right?
Yeah, I think that there he was just showing the initial stage of the evaporation process. So, for example, the entanglement entropy was rising,
Right.
and in that case, I think at some point it should go down because it's a lattice model. It's a 1D system is unitary, and I was discussing with him and. There, I think that the problem was that it then didn't have enough control on the system to somehow create a black hole which actually can evaporate.
But it was still quite intriguing that the thermal distribution seemed to come out there.
Yeah, no, indeed. And actually, I think in that case it would be interesting to kind of like go back, like try to work a way to actually sort of like create a black hole and make it evaporate, and somehow try to learn something for the quantum gravity case. And but yeah, to some extent here we are kind of like going a bit we're taking a different route in the sense like we are not trying to find a mistake in Hawking calculation because we know it's going to be very hard because you have to know what is the microscopic theory. We're just trying to find effective ways of computing the entanglement entropy. And it seems like gravity tells us that for some reason we also have to include these disconnected regions that that are like inside the black hole. But for example, from the boundary conformality theory, that is just a 2-point correlator, and it's just constant unitarity.
Any more questions?
The role of correlation function was that I'm very against history because it's really analogous to the Takanari formula computing just using the same prescription.
In what case? Sorry?
Correlation functions appear because you compute them with the same prescription that you Takanari formulas.
Exactly. Yeah, and correlation function appear because you can, at least in two-dimensional CFTs, you can compute entanglement entropies with twist operators. So it's basically the correlation function between twist operators and I mean, it's not exactly the correlator. You have to that I think computes the trace of rho to the end. It's like a Rényi entropy.
Okay, let's thank Pietro again.